Hi, my dear students. Good morning, everybody, and hope you are enjoying the classes of thermodynamics, which is a part of your life and which is happened in your everyday life. So today we will discuss about the second law of thermodynamics. Because we have already discussed about the first law of thermodynamics and its application and its consequence and its limitation, etc. But today we'll discuss about the second law of thermodynamics and the Carnot cycle. So today we'll discuss about the two things. One is the second law of thermodynamics, another is the Carnot cycle and its efficiency. And then if we get more time, then we'll discuss the absolute zero temperature. So student, here again I am Dr. Biswajit Gain, Assistant Professor, Department of Chemistry from your college, Dr. Sudhit Chandrasur, Institute of Technology and Sports Complex. Here you are seeing in the picture a diagram of Carnot cycle. So I will discuss detail uh, in some next few slide about the Carnot cycle. Before going to details about the Carnot cycle, we have to know about the second law of thermodynamics and its understanding. We will start our study with take a very common example of our life, that is refrigerator. So yes, in I think most of the student and in their room there are refrigerator, that is we very simply call it fridge. But it is recommended that you should shut the door of fridge always, because if you keep it open, so then it will be not beneficial for you. So suppose I am coming from a hot situation and now I am open the door of the fridge and I am standing in front of the fridge. Yes, you will feel some coolness because the inside of the fridge is cool and your body temperature and you are feeling hot, so there will be heat transfer from your body to fridge, so you will feel some cold situation or you feel cool. But if you keep the door of the fridge always open and mainly the refrigerator are placed in the kitchen and your kitchen is on, then you will get a heart stopping electricity bill. So your bill will be electricity bill will be abnormally high, because the freeze is a small system and they are cooling the system within particular small volume. But if you open it, then the kitchen and the freeze will be an open system, so there will be a heat transfer from kitchen to your freeze is taken place, and there will be a huge amount of the heat exchange will be happened, and your refrigerator will be work hard to minimize the thing or absorb the heat. So then your fridge will be act much more, and your electricity bill will be, you know it better, so electricity bill will be abnormally high. So this is the case of the refrigerator. So in refrigerator, that means if we think that okay, I will keep the refrigerator open and I feel cold, but no, it is not possible to make cooling in the refrigerator. There need of energy, there will be a need of energy, that is electricity. Then the refrigerator become cool and it will be function. So if you keep or worked hard on the refrigerator, then it must consume more electricity. So a more electricity is required to work hard the refrigerator. So without this work done, or basically supply of the energy, you cannot supply heat from cold to hot side, or just opposite. So this is I just describe you the real example of the refrigerator, and also this is a uh, example of the second law of thermodynamics. Now I want to say about the second law of thermodynamics. There is no concrete second law of thermodynamics, but the concept is same as always, but the defined scientists give the definition of the second law of thermodynamics in defined mode, but their actual goal is same. So here Kelvin Planck. So Kelvin Planck give a statement about the second law of thermodynamics. Basically, they give the statement, and we are using their statement as a second law of thermodynamics. So they said it is impossible for any system. It is impossible for any system to undergo a process in which it absorbs heat from a reservoir at a single temperature and convert the heat completely into mechanical work. So if it is impossible from for a system to work in such a way that it absorbing heat from a reservoir and converting 100% work, so this type of the system or engine is not possible, the system ending with the same state as it began. So suppose we are doing the same thing and it is a continuing, that is we are taking the heat and working with 100% efficiency. So it is not possible according to the Kelvin and Planck. Yes, it is absolutely right, it is not possible. Now another statement, that is Clausius statement. So here he said it is impossible for a process to have its sole result for the transfer of the heat from a cooler to hotter part is impossible. So just this is the very real example of refrigerator. You are trying to transfer heat from refrigerator to, that is refrigerator to oven or the kitchen or to you, to your body. But in that case, it is not possible. It will be possible if you, or if you arrange in such a way, then there will be work done on the refrigerator, then it will be true. But without work done on the refrigerator by electricity, then it is not possible to transfer heat from refrigerator to your hot body. So this is the thing. So here is the diagram. It is much or less complicated depending on your understanding. So here, if you look to the right hand side figure, so here the heat is transferred from the TC is here, the blue region is called the sink, and the sink temperature is low, and the orange is called the reservoir. So the temperature is high. So there will be a transfer of the heat from sink to reservoir, that is the orange zone, is impossible without doing any work. But if you make some work, if you go to the left hand side, if you do some work, then this transfer of the energy is somewhat possible. Now again another thing, that is you are absorbing heat from the reservoir, that is the right hand image, absorbing heat from the reservoir, and you are converting it to the 100% work. No, it is not possible. You have to supply some heat to the sink, then only it is possible, because 100% conversion of the energy, that is heat to work, is not possible. Then the transfer of the energy to the sink is required. So in the right hand side, yes, it is possible, that is it absorb some energy and make some work and transfer some heat. So yes, it will be possible. Now we want to enter another thing, that is the application of the Carnot cycle, and from that we'll also define the entropy as another parameter, very important parameter in the thermodynamics. So student, here Carnot cycle, yeah, this is the diagram of a Carnot cycle. It is a cycle because the process A, B, C, D to A is a cyclic process. So this, and the Carnot is one of the scientists. So as it is the cyclic process, so that's why it is called Carnot cycle. And this cycle or this process is maintained by taking the gaseous system, and we are studying a phenomenon of its efficiency and other thing. So here if you look to the diagram, so there's a pressure volume diagram, and if you consider state, then there will be four state, that A, B, C, D. Now state A to B is an isothermal process, and there is a absorption of the heat, but state and the expansion of the volume also. And state B to C is also an expansion of the gaseous system, but it is a adiabatic process. So here the internal energy is used for the expansion. Now again C to D is an again isothermal process, and here is the compression takes place. And D to A again is a adiabatic process, and also a compression takes place. So these are the details about the process occurring in the Carnot cycle. So I have already told you what is happening in this diagram, because that is state 1 to 2 or A or B, nothing. So there is a Q amount of the heat absorption, and by absorbing heat, it expanded the gas, and the temperature along this A to, sorry, 1 to 2 is the constant temperature, that is TH. And now the 2 to 3 as the adiabatic process, and as also a expansion of the gas, so uh, it will it will be done by the expense of the internal energy, so the temperature will be decreases and it is reaches to the TC. Now 3 to 4 again is the isothermal, so the temperature will be fixed, that is TC, and there will be a compression, that is the loss of heat. So in the last stage, that is 4 to 1, that is again adiabatic compression. So here the internal energy will be gained because there is a compression. So now we want to correlate or totally uh, want to calculate the total work done and total heat absorbed. Then we will need to go for the calculation of the efficiency of the circle. So there will be a student, there will be some problem in the slide. So now I want to shift another slide, that is this. So here internal energy is no change because the temperature is fixed from 1 to 2, and there's absorption of heat, that is Q 1 to 2, and work done, the heat and work done, if it is the ideal case, that is RTH, that is the temperature is H, and ln V2 by V1, that is the V1 is the volume at point 1 and V2 is the volume of the point 2. So here the heat is absorbed by the system is converted to the work, and work is equal to nRTH ln V2 by V1. Now again in the transformation from 3 to 4, del U is 0, and it loss it heat, that is Q3 to 4, and it is loss or work done will be negative, that is nRTC ln V2 by V3. It, it is a negative sign because the work done is negative because it is less than 0. Okay, so now this is the this T B gamma minus 1 is the expression for an adiabatic process. So there will be correlation of the T1 to T4 and T2 to T3 because both two are the adiabatic process. So here THV1 gamma minus 1 is equal to TC T4 gamma minus 1, and another same thing for the 2 point, that is point 2 and 3. So from this expression we can reach a expression that is th by tc is equal to v2 by v3 to the power gamma minus 1. So now again, from the total cyclic process, v4 by v1 is equal to v3 by v2. So v2 by v1 equal to v3 by v4. So v2 by v4 v1 may be replaced by v3 by v4, or v3 by v4 is replaced by v2 by v1. That's it. So now if we divide the heat absorbed and heat loss, that is q1 2 by q3 to 4, then it will be nRh ln v2 by v1 nRTC ln v4 by v2. So if we replace it, that is v4 by v3 by v2 by v1, then it will be same and it will be just negative. Then the final expression will be th by tc. So this is the final expression. So now the Carnot cycle or Carnot efficiency is basically the work done by heat absorbed. So in this Carnot engine, the heat absorbed is QH. Okay, that is in the process of 1 to 2, and work done is basically W. So again, W is equal to QC plus QH, because it is the whole work. Some is in the first cases it is positive, that is q1 to 2, and the next case is q3 to 4. So basically qc plus qh by qh. Now if we simplify this equation, then it will be 1 plus qc by qh, but the qc and qh are opposite in sign, and if we replace this thing, that is qh qc here, that is minus th by tc, then it will be ultimately, as there is a c by h, so that will be minus tc by th. So very simply now we come to the conclusion, that is the efficiency of the Carnot cycle is 1 minus tc by th. So 1 minus, so here the tc is the low temperature and th is the high temperature, so there will be a fraction. So but it is always 1 minus something. So from this expression it is clear that the Carnot cycle efficiency is always less than 1. And yes, for any kind of the engine the efficiency cannot be 100%, but it always less than 1. Carnot cycle is a completely reversible, because it is a reversible process. Again A B C D, again it come A B C D following the path. So run backward, it is a Carnot refrigerator. So if I make that just opposite process, then it will be acts as a refrigerator. So this is the mathematical problem and calculation of the efficiency. So here by using this slide you can calculate the efficiency, and you will always obtain a efficiency less than 0. So student, today is up to this. and next day we'll discuss about the details of the Carnot cycle and the entropy and the absolute temperature. So hope you are enjoying the class and you are satisfied with this class. And in this situation of COVID-19 and this rainy season, take care yourself and your family. So student, thank you very much for your kind attention in my class, and I am waiting for your response. This response may be your suggestion, response may be your queries, your problem. I am waiting for your response. Thank you very much again.